Hello and welcome back to another coding session with Mr. Jacob. Today I want to use our PixelLoop engine, which we developed before. It will be linked up in the corner if you don't know about that, to implement a simple rendering of a Mandelbrot set fractal, to simply play around with that, because I've actually never rendered a Mandelbrot fractal set. And I thought maybe it is time to do that together with you. So let's get right into it. So what is the Mandelbrot set? So the Mandelbrot set essentially is, as it is described here, a two-dimensional set with a relatively simple definition. Okay, we will see about that, even though in this case it is relatively simple. And it is a fractal structure which is defined in the complex plane. So we will be talking about complex numbers. We will have to keep that in mind. As the complex number here c, for which the function fc of x equals z to the power of 2 plus c does not diverge to infinity when iterated starting at z equals 0. So let's think about that and let's think about what that means. So essentially, we are starting at a z equals 0. So we are essentially putting a 0 into this z here and calculating this thing with c, where c is a complex number. So first of all, let's check out what a complex number actually is. And be prepared. I unfortunately can't do the next step of this video in dark mode, so be prepared for a white background. Okay, so I'm sorry for that, but I unfortunately can't change that. And it's the only thing that I found to actually be able to properly write here. I hope this will be okay for you. So please give me feedback if this kind of explaining and working works out for you. So what is a complex number? Essentially, a complex number is something that has a so-called real part and a so-called imaginary part. So we have something like, for example, 5 plus 4i. And this 5 plus 4i is actually called one complex number. So this thing here is a complex number. Okay, so as this is a complex number, what is this correlation of things here? It is essentially something where we have this part here, the 5, which is the real part actually. And we have this 4 part here, which actually is the imaginary part. So this is the imaginary one. So what is this I here? I is actually simply a definition of a square root of a specific value. So what is I? Let's see. I actually is here in this case defined as the square root of -1. And now you might be thinking, okay, what is this with the square root of -1? This doesn't make sense. You can't do something like you cannot square any number, any real number, and it will be in the end the result of this. So what are we doing here? And that is exactly what we are doing here. You can't really define, or you can't really have a real number which is the square root of -1, because this simply does not work. But if you go ahead and define simply something like I is equal to the square root of -1, you can do a lot of neat little things with it. And that is exactly what a complex number is. A complex number has this real part and this imaginary part, and this imaginary part is always combined with this I value that we simply define to be the square root of -1. So it is simply defined to be that. And what is interesting about that, so to speak, what is if we go ahead and do a squaring of I, we would actually get -1. So keep that in mind, because we will later on use that when calculating this fractal. Okay, so we now have this structure of imaginary numbers, and imaginary numbers in general are usually defined as something like a plus bi. So this is actually an imaginary number. Sorry, a complex number, not an imaginary number. yeah, let's remove that again. That is a complex number here. So that is usually taking this form, like the A and the B. And now when we are going about this, we can actually kind of try and use a two-dimensional display, like for example our display canvas here. We could do that by, if this is our canvas here, canvas, we could actually use these A and B values as coordinates in our 2D plane, because that's what a complex number is. It is a number in a complex plane. And therefore, we could do something like, say, all of our X values, for example, are the A component, and all of our Y values are, for example, the B component. And there we go. And then we could try and render that. We could try then and render a complex number. But now let's see what actually this fractal is there, that we really want to render there. So the Mandelbrot set has now, as we know what this C is, it's a complex number. We are essentially going ahead and starting with Z equals 0. So let's just take this f of Z equals Z squared plus C and see what happens if we put this into each other. To do exactly what is put there. So f of z equals z squared plus c. So what does that actually mean if we start with z equals 0? So we would have f of 0 equals 0 squared plus c. So essentially, that would mean that this is simply C. So we start with a C, and C is our complex number. And now in the next iteration, we would actually put this result that we got there, the C, into our function there. So we would do something like, we would do something like f of, in this case, f of 0. So we put that into each other, would equal c squared plus c. So we would essentially need to kind of calculate that, get a complex number out of that again. So we somehow need to calculate that here, this result. And then we take this one and put it into the function again. So into the z squared plus c again as a z, and go on and go on and go on. And then once we are doing that, we actually check that the number does not diverge to infinity. So, which actually means is if we are going to iterate indefinitely, would the number simply grow to infinity? And of course, when we are calculating this in a program, we will not go to infinity, but we have a certain amount of steps and just see if it's going out of some sort of bounds there to actually create these images here. But essentially, the set of complex numbers, so our canvas, so to speak, which consists of those that are not diverging to infinity when we put them into this formula and calculating a lot of steps, like, I don't know, maybe 100 or something like that. We will see that when we calculate that. Are actually part of this Mandelbrot set, and all the others are not. So that is actually what we want to calculate, because when we then draw it, it should actually give us a picture like that. Maybe not that colorful, because we can choose the color values there, but it should give us the pixel representation of this fractal here. And even if we then kind of zoom into this, like this, for example, it should give us all of those nice, neat little values of those this set, because we can, of course, do that with decimal numbers and not only integer numbers. Okay, so what we are going to need to do here is now we need to somehow calculate, that's our point here, what this C2 actually is there. So we need to know what this actually is. How do we calculate that? We can simply go ahead and try that. So we know that it is a complex number. So C is A plus BI. So what is C squared? C squared is A plus BI times A plus BI. So what that actually means is that we can simply multiply all those different components there. So we have a squared plus abi. Then we need to go to the next value in the first bracket. So we have, again, abi, or more specifically bia, but I've just reordered that, plus b squared I squared. Because we are multiplying bi with bi, which is b squared I squared. Okay, so now let's go ahead and put that together even more. So we have a squared plus 2abi plus, and now let's think about that. As I've told you before, I equals the square root of -1. So I squared equals -1. So what we can do is we can put that into there. So what we now have there is we have -1 times b squared, and therefore we can simply make this not a plus, but we can make that a minus b squared. And if we now simply reorder that, because now we only have one I in this formula, we can do a squared minus b squared plus 2abi. And can you see what we now have here? We have again this part, which is a real part of our complex number, and we have this 2ab part here, which is the imaginary part. And we have, all in all, a new complex number. A new complex number which has the a part, the real part is the a squared minus b squared, and the imaginary part is the 2ab part. So essentially what we have here in the end, this is a new complex number which we can then use again to be put back into our formula here. And now we actually have everything that we need to know to go ahead and implement that. We have a way of implementing this kind of loop, or the needed information there, and we have our set to be calculated there with this this definition here that we have seen before. So let's go ahead and try to implement that. We will come back to this formula, of course, to refer to it when we are implementing that. So I have already created an empty folder here. So let's quickly initialize a new cargo project, a new Rust project in there. And let's see, now we have this Rust project here, and we need, of course, our PixelLoop engine. So let's quickly add that. Perfect. So now we should take a quick look and copy out one of the examples of our not cargo RS of crates.io. Let's see, and let's go to PixelLoop. And there we have our PixelLoop engine, and where is our link there? Let's quickly take one of our examples here, because I think this one is the easiest one to just go ahead and start everything up. Perfect. Let's take this one, and let's just copy out the code of our example to speed things up a little, because we already talked quite some time here about how this Mandelbrot thing is going to work. So let's put that in there. There we should have all of our different canvases. We are not going to need any flying boxes. We are cleaning up our state here. For now, our state will simply be go back. What did I do there? Our state will simply be an empty self here. Perfect. And we might want to do something like 800 by 600 for the size. We don't want any scaling here. We can simply call this one, how did I call it actually. I called it PixelBrot, didn't I? So, as it is a Mandelbrot fractal. So yeah, PixelBrot. You get the gist. So yeah, most likely on keyboard press of space, we will want to do something. Otherwise, we are not doing anything there. Let's remove that. Let's do the rendering. We don't want to render any flying boxes. But we want most likely to clear the screen in black. And now, did I really miss? Yeah, I really deleted, I guess, here somewhere. Yes, there I deleted brace. So we don't need randomness anymore. And yeah, we need to install anyhow, I guess. So let's quickly add cargo add anyhow. Let's quickly add anyhow. Maybe get a new shell here, which we can then use for our editing, and one that we can actually see and execute our program in. So now we should actually have this proper run state here, which does nothing to us but display a black window. Let's quickly check if it does that. Cargo run minus release. Let's quickly compile that, and then let's see that it really displays to us this dark and black window with only black pixels at the moment, and then we can go ahead and render things. Okay, this seems to work. We now have a PixelBrot application here. However, let's directly change one thing. It is configured to be resizable. I don't want to actually care about that first thing there, so I just disable that. Okay, so now let's go ahead. Let's implement something that would render our Mandelbrot structure here. So let's go ahead. Let's maybe create something like a Mandelbrot struct or something like that. And what would that Mandelbrot struct need to hold? It would need to hold for each of our canvas pixels the divergence value. So if this function that we have seen here, let me go back there, not to the example code, but to our screen stream here. So this actually, come on there. Where is it? This so for each of our, where is it? There. For each of our canvas pixels that are in this complex number there, we want to actually hold this number that the divergence, so the calculation of putting all of those functions in each other again and again and again holds, because that's actually how the color here is created, or how we could create grayscale or something like that. So the speed with which it diverges is actually used for these nice color boundaries. So usually, at least. So so we kind of need that. We need a width and a height, definitely. So let's do something like divergence. How is actually that written? Wait a second. So diverge, yeah, nice. So how is divergence written? I'm not sure that it is really written like this. So if it's not, I'm sorry for that. So this would be a vector, I think, of F64s. We need a width, which is a U32. We need a height, which is a U32 as well. And yeah, we'll see what we need as well. I guess we will need some sort of zoom value or start value or end value or anything like that. But we will see how this actually needs to turn out. So let's quickly implement our Mandelbrot here, and let's just create a new function quickly, which takes a width, U32, a height, U32, and that should be it. And it should return a self, and then we can do self with height, and divergence will be a simple vector here, which has 0.0 at every position there, and it has width times height elements. And we need a semicolon here, of course, for this to work. And this should actually create us, oh yeah, the amount of elements, of course, needs to be a U size. But this should definitely be a U size, otherwise we could not, we could not even allocate that. So, okay. So then let's see how we would actually render something like that. Maybe let's do and go ahead and create something like Mandelbrot here. Mandelbrot will be a Mandelbrot new, and I guess we will path in the width and the height here. So we will put that in here with U32 height, U32 just past that. And the state, of course, now needs a Mandelbrot property. So something like Mandelbrot here. Okay, so now when we actually create that state, let's do a width and a height here. And okay, what are we actually putting in here? It's a U32, so I'm not sure. Okay, just some sort of not updated error thingy there. I definitely want something like if I is key, come on, key pressed, keyboard key Q. I want to return, okay, next, come on, next loop state. What was it? Exit? I think it is exit. And we just do a 0 here, something like that. Okay. Yeah. Of course we can remove that, but let's do to do so that it shuts up about that. Okay. So now what we want to do actually is, do we want to render anything? No, not yet. We need to now implement some sort of rendering. We have now our Mandelbrot structure there. So let's implement maybe our render function here. So let's call this one render, and it will simply calculate all of those divergence values. And yeah, now I remember why I actually implemented this here for the pixel loop in the first place now, because I wanted to use the divergence values that we are going to calculate here to actually display something to the screen. So we are assuming that our divergence values are there, one for each screen pixel. So we are going ahead, I guess, and are iterating for each of these screen pixels there. So we are doing Y in 0 to height, and we are doing an X in 0 to width. And we are then iterating that, and we need, of course, some sort of index there that we can easily calculate now as we have X and Y. So it will be Y times the width plus the X. That will be the actually the excess value into our divergence values there, and we want this one as a U size. That's already quite clear. And now we can get the let divergence equals s dot Mandelbrot dot divergence at position ID X. We want that value. And now we could do something and create a pixel value there corresponding to this divergence. So I guess we will store how many iterations it takes for this function to kind of escape some sort of big value that we will set. And we will then see how long this takes. And we could actually maybe create some sort of brightness value out of that. So brightness equals divergence. And now we would need to know how many iterations we are actually doing. So let's go back to our Mandelbrot set and let's iterations. Let's add something like iterations and maybe do just 100. We will, I guess, optimize that anyhow. So iterations would be a U size, I think. Okay, so now let's go back to, where were we? Come on. So now we could take this divergence and we can, I guess, divide it by as Mandelbrot iterations as f64, and we do times 255, I guess. So now we should actually have mapped this from the iteration kind of space that we have there, where we count our iterations, into our usual color value there. So now we should be able to do something like canvas set, just set, just set, and we will do x as u32 and y as u32, and we will need a color here, color, which is actually, is this actually our representation of a color? I'm not 100% sure there. From RGB, and this one would be brightness. So everything that's in the set, so everything that does not escape our calculation, which we will do in a second, should actually be black, and everything else should get more and more white, so to speak, if I've done this correctly. And I guess I need to now import this one. No, I don't. Oh, yes, I wanted to add a reference here. Thank you, LSP server. So I think I just did not bright. Oh, holy shit! What did I do there? Bright. There, like this. Okay. And we need Mandelbrot here, of course. And now what's the other arrow here? Cannot multiply. Yeah, we need as f64 here, and then in the end we will simply go ahead and do a floor here and do as u8. As u8. Yes, we need those values as u8s. Yes. Try x. Wait, what? What is it going? Casting to the same type is unnecessary. Oh, those are already U32s. Okay, nice. And what's the problem here? What's it referencing here? Casting integer literal to f64 is unnecessary. Yeah, that's absolutely right. I could just have done like this. Okay, perfect. Now we should actually be able to render that stuff, and as we do not calculate anything yet, it should simply stay black. It does. Perfect. So my Q works as well. I've just pressed Q and it ended everything here. So yeah, let's see. How do we now actually use our calculation here to render something? We now need to do this calculation that we had prepared here. So where is it? Screen stream. So essentially what we now need to do is we need to over and over do this calculation here. So we put in our initial A and B values, which are the canvas width and height values. And for each of those values, we do this check, and we do it iteration amount of times. And once we have reached this iteration, we will see if it, or even before, we might even see it before, if it leaves this specific space. So what we are going to do here is for y in 0 to self, and of course render needs a mutable self here. Yeah, I could have thought about that. So I need a self height, and for x in 0 to self width, I want to iterate. And what's the problem here now? What is it? Interesting. It's kind of... Okay, there is something wrong with my VI setup. So let's just restart that quickly. Something with the LSP, I guess. Strange. Okay, there we are back in the editor, and everything seems to be fine again. There was something really broken with my VI session. Okay, so we are going to render this for each of the pixels. And essentially what we are going to do is we are saying that we have an A value here, which we start as the X value, and we have a B value there that we would start as the Y value. However, and that's something that we need to think about, if we are actually using the real x and y, so if we are actually using the real x and y values for our a and b values here, we would have values from something like 0 to 800 in the A, and we would have something like 0 to 600 in the B direction. And I don't think that is a good idea, because actually this Mandelbrot set, or what is like that, is usually, I think, in the range of kind of like -2 to 1 or something like that. If I remember correctly, that's kind of the 0 point here. I'm not 100% sure, but so what I actually want to do is I want to do something like I want to have a from kind of maybe, yeah, -2 actually to 1, and I want the same actually for the y. So we need to somehow map our values between -2, or our pixel values to -2 to 1. So let's first of all quickly do that. Where's our, there it is. So we should actually now easily map that. So let's do something like mapped, mapped x, which would be the x value as an F64 times the range that we are actually going to map it to, which would be 3 if we are going from 2 to -2 to 1. We would be in the range of 3. So we are multiplying this with 3 and then dividing it actually by the width, don't we? Yeah. So self width as an F64, and this should actually then map it to the range 0 to 3, and as we want it to map to the range -2 to 1, we will actually subtract 2. And this should give us our mapped x, I hope. And we can do more or less the same thing with the y. We are doing more or less the same thing. However, we are here, of course, dividing by the height. And then we are subtracting 2 as well. And we will see where this actually gives us, what this will actually render for us. So yeah, let's go here and let's do something like mapped x here and mapped y here now as a starting point, so to speak. And now we need to do for I in 0 to self iterations. So for each of those iterations here, we now want to see if this calculation actually escapes, kind of, if we put it over and over into each other. So we need to calculate those values. So what do we actually need to calculate? Yeah, we need to calculate exactly what we had here. So we need this a squared. So this a squared minus b squared for the x component, and this 2ab for the b component. So let's calculate that. Let's calculate that by, maybe we could call it new a and new b. So new a will be a squared, so a times a minus b times b, because b squared. So this will be our new a, and we will have new b, which is 2 times a times b. So this is actually exactly what we had here. So a squared minus b squared plus 2ab. And this will be our new a and b values there. At least part of them. Okay, so we have now calculated those, and we now need to kind of update our initial values here, which, by the way, don't start with a mapped thingy here, but are simply 0 at the beginning, because as we remember, the Mandelbrot set definition said, where is it? that it starts with fc of 0, and we start with z equals 0. So this will actually be no, that's not right. Actually, we start with our mapped values, because we have this c part here, which we actually have there, which we will have there. So we have 0 plus c, and c actually is the imaginary number, the complex number that actually represents our screen coordinate in this case. So we have that. However, we could now simply do some check how large these values are actually. And if we have a certain largeness of this value, so to speak, we could define that it is diverging. And that's exactly what we will be doing. However, we need to, first of all, as I've said, update the A and the B. So we are doing this again and again and again, and putting each of those functions into each other. But what's with this C there? So if we take a look again here now, we have this z squared plus c. So we always have this z squared. That's what we just calculated. But we need to add c to that. So what we need to do is we need to add to each of those values that we have here, in the end, our c part. So that is our initially mapped value. So we have something like mapped x here, and we need to add mapped y here, because that is our x component and that is our y component. So the a is our x as we defined it, and y is our b component. So now we can do a equals new a and b equals new b, and we will of course need to make those mutable in a second. No, I don't want the Vim help, thank you. I really need to remember this key. I'm going to press it over and over again. So, okay, so now we should actually have those updated. Yeah, and now we need to somehow check if those new A and B components go into a certain direction. Like, for example, I'm not sure that this is a good value. We will see in a second, something like 16, or maybe even lower values will work. So usually those values are pretty small actually that happen there if it's not diverging. So it usually should work out for us to actually calculate this, and we may even be able to get away with something a lot smaller than that. However, we need, of course, the absolute of those values. So what we can do here is we can do something like if a dot abs, come on, plus b. No, we actually need something like a plus b, and we need that. Is that actually true? Do we? Actually, we only need the we need the absolutes before. So we simply do something like a abs plus b abs, so the new values here. And if this is, for example, bigger than, I have no idea, 16 or maybe even 4, or we will see. We will see. If this is the case, then we assume it is diverging. So in this situation, we are simply doing a self.divergence. And now we need, of course, the index, which is y times self width plus x, and this as a u size. Let's do that as u size. And we just put in the amount of iterations that we needed to actually make this thing diverge. So we have actually something that we can display in this brightness level that I showed you before, or that we implemented before. Okay, and of course, when we start this, we actually want to put all zeros into the self-divergence array here. So self-divergence, is there actually something like, yeah, there is actually something like fill cells with element by cloning value. Sounds beautifully perfect for me, because we can simply fill this up with zeros there, so we kind of clear it. And there we are going to be told that expected due to the type of this binding, you can cast the U size to a producing floating point. Wait, what? The divergence is actually... Oh, we defined this as a floating point, but we actually store that in a, we can store that as a use size, I think. I think we can even store that as we keep it below. Yeah, this and that need to be the same data type, so we could actually go ahead and do that with an U8 or something like that. Yeah, but that should actually work. So then we need, of course, to fill that with just 0, and we might want to do the same thing here, and then I think this should now work out. Yeah, okay, so now we have this divergence there. So why did I cast that into float here? Oh, yes, of course, I cast it into float to not lose precision here. But yeah, nevertheless, I don't need it to be stored as divergence. So if we did everything right, we could now do something like put an S Mandelbrot.render in here, and if we did this right, and if my values here, like the 100 for the iterations and the limit, which we could actually put into here maybe. Okay, let's do that. So divergence limit is like 16 or something like that. And we will have a divergence limit here, which is an F64. Then we can actually use that here. Self-divergence limit. Come on, self-divergence limit there. Okay, so now we should maybe have a Mandelbrot fractal on the screen if I now press space. Fingers crossed. We have a Mandelbrot fractal there. Okay, it's not perfect there, but we did some Mandelbrot fractal rendering. So I think we want the y to start at 0, not at -1. Maybe we should change our mapping there and then just go from 0 to 2. Maybe looks kind of okayish for me then. And we may have kind of squished things a little. Not 100% sure why this actually happened, but yeah, so if we simply go from 0 to then, we don't need that anymore. So let's see how this now looks. Okay, now we are completely off. Okay, so maybe I want to go from -1 to... do I want to go from -1 to 1? So -1 or something like that? Ah, come on. Hey! -1. Wait, what? Whoa. Okay, let's do that again. Okay. Sorry, VI, what are you doing? Oh, I was in the... Yeah. Okay, I was simply in the wrong Tmax pane. Okay, so this looks a little bit better, even though our scaling is a little bit off. Maybe we should simply do something more squarish, which would, for now, make things easier for us with regards to scaling. So I think what we could do here is we could do and scale the things equally. So we will do the 3 and 2 here again. Or even maybe we do just 2 and go 1. So now we should be, or maybe 4. Yeah, let's maybe go from -2 to 2, and let's create the whole PixelLoop thingy here, not 800 by 600. Where the damn is that? 800 by 600, but maybe just 800 by 800. So this way we don't need to calculate aspect ratio and stuff like that, and it should actually, yeah, it should look properly there. Okay, so we have a Mandelbrot fractal now, but the really nice thing there would be if we could actually zoom into that. So let's see if we can quickly implement that. That should actually be possible. Do we really want to do it like that? I think I want to define the ranges and the zoom level there, but I think the stream is already long enough here, the video. So let's maybe just zoom in manually by simply selecting a neat little part of the Mandelbrot fractal here. So what would be kind of neat? So let's see. I guess I did this last, didn't I? And this worked out quite nice and looked a little bit nice. So actually, I would have loved to be able to zoom into that, but I guess, yeah, I guess our time is up for today. Yeah, maybe I will just change that in the code and in the aftermath of this video. So and implement kind of, I guess, zooming there. That shouldn't be too hard if my head is clearing up again thinking about this, as clearly need to drink something and eat something. But yeah, nevertheless, you now know how to actually implement Mandelbrot fractals, and actually using this divergence information and how fast or how slow it diverges and something like that, you can easily think of how you could actually implement some of those nice, neat little colors there that you see everywhere when somebody renders fractals there. Maybe we will come back to this topic and create something that renders us a neat little fractal zoom in animation and kind of renders this to a video. Maybe you would have interest in seeing me do that, integrating something into our PixelLoop engine that would be able to export such an animation into a video sequence. That's something that I'm thinking about for quite some time now, and I'm thinking that could be a neat little video there. So if you would be interested in that, definitely give this video a thumbs up. Please subscribe and leave me a comment there. And I hope you had as much fun learning and thinking about how to implement fractal rendering here, or Mandelbrot set rendering here, as I did. So yeah, I hope to see you in the next one, and bye!